Now turn to numerical methods for solving hyperbolic problems. We consider the following wave equation: UTT equal to UXX. So in this case, C is assumed to be equal to 1. It's a normalized wave equation. X is between 0 and 1, and T is, as usual, larger than 0 or equal to 0. We have an initial condition, initial displacement, which we as usual call f of x, and then initial velocity, the partial derivative of u with respect to t, which we call g of x. The boundary conditions are as usually equal to 0. That means that we have fixed the string on both sides. So if we use h as the discretization step in x direction and k the discretization step in t direction, if you want to call it the t direction, then we obviously get this discretization equation. Because we remember that uxx is equal to this, and of course when the discretization step is equal to k with respect to t, then we have this on the left side. We will assume that r star, which is defined by k square over h square, is equal to 1. So we have equal step length or step in the two directions, both x and t. In this case, we obtain the following discretization equation. So, for example, if we put I equal to 1 and g equal to 1, then we obtain the following discretization equation. Just replace I and g by I and j by 1 and 1 respectively into this equation. We obtain this equation. And here we see that the number 1, 2 refers to this point. 0, 1 is this point. 2, 1 is this point. And 1, 0 is the lower point here. So if we knew all the values on this row, then it would be easy for us to find the value in this point. So the only thing we have to do in order to find the values here is just to find a method for finding the values of u on the first row here. And how are we going to do this? Because we have a problem. If we want to put I equal to 1 and j equal to 0, then the following happens. Just replace I and j equal to 1 and 0 into this discretization equation. We obtain this equation. And this is no problem, these two values, but this value is a problem because we do not have any point 1, 0, 1. So what are we going to do with this point? Well, we do as we did for the parabolic problem. We make an auxiliary point here, a virtual point if you like, and imagine that we that we had some temperature at this point. Then we recall that the derivative of u with respect to t may be written as an and then we mean the derivative in the point 1, 0. Actually here can be approximated as follows. We take the value in this point minus the value in this point, and we divide with 2k, that is the length, the distance between these 2 points. So this will be an approximation for the derivative with respect to the time in this point, and we know this value because it is the initial velocity, g1. We call it g1, where gi is defined as the function g of ih. So ih is x. So this can help us, because then we can just multiply this equation with 2k on both sides, and we obtain, we can then express u1, this virtual value as 2k g1 minus u11. So if we insert this expression into this equation, then we obtain the following. We obtain this equation, and now we are able to solve this equation with respect to u11. So then we have the possibility to find u11, and in fact we have the possibility to find u in every of these of these points, and in fact it's like this: u I1. You know, every point on this row can be written as u I1. It will be exactly as above, written in this way, only that we take in the first coordinate here is replaced by I minus 1. So this equation can be used for all these points. So when we know the value in all these points, we just use this equation for the next row in order to find the unknowns there. So then we have solved the problem. We are going to give an example where we use this method very soon.